First, good afternoon. Thank you, Improvate, for inviting me. Happy to be here. I think we'll have something that we could send around the world in Gadfin. Precise is leading or pioneering a new area of tissue engineering, of the fabricating of tissues. And if we look at various trends that we are aware of in healthcare today, so we're familiar with remoteness, and we're familiar with the fact that people are living longer. And when people live longer, you have things go wrong, and you have to replace a spare part. And essentially, if we look forward, if we look forward 10, 15 years, we will have a whole field of biofabricating of tissues and organs. And our vision here is, instead of that people today have to wait for somebody to die and donate an organ, we will be able to fabricate these tissues, fabricate organs with 3D printing and other technologies, and we'll be able essentially to have limitless supply of tissues to go around the world and to bring them to the patients. So we are in a new era of bioprinting. As I mentioned, 15 years looking forward, we will be printing hearts, we will be printing kidneys, but these are complex tissues and complex organs, and it still has to mature, and these technologies have to evolve until we will be able to look forward and be able to fabricate complex tissues. Precise Bio here is essentially taking regenerative medicine and technologies that have been developing over the last 2 decades and bringing them together with 3D printing, where we fabricate tissues and organs. And our goal is really to bring these tissues to the hands of the clinicians so they can transplant them in the body, in the patients, and replace damaged tissues or diseased tissues from one aspect, or in places where there isn't sufficient supply around the world. And here we can fabricate tissues in a sustainable, repeatable, and scale-up method to bring tissues to the patients. How do we do this? We started out with 3D printing technology, unique technology that we patented, and it has single cell resolution. We can deposit cell by cell, and this way we can mimic the anatomical structure as the tissue is in the body. That's where we started, but we have cell technology, and at the end of the day, the main building block of any tissue in our body is the cells. The cells can be coming from stem cells, primary cells, or other sources. Their biomaterials, our tissues and organs are not just comprised from cells, but there's ECM, extracellular matrix, other materials that structure the tissues. And to bring all of that together is really a task of bioengineering. But even after we have the tissue and we have the cells in place and the ECM in place and all the materials ready, we still have the capabilities to test it, to make sure that it functions before we put it into the body. And here is where essentially a lot of engineering tasks come in. So it's engineering not only at the beginning in the bioprinting, but also in the QC systems. Today, when we take a cornea from a patient and we assume that since it worked in one human, it will work in another human. But when we take a cornea from our 3D bioprinter, we have to prove that it's transparent. We have to prove that it's flexible enough. We have to prove that it has the strength and the cell density. And here, essentially, there's a lot of engineering technologies that come in together and enable us, at the end of the day, to take these tissues from the cells all the way to the clinic. What you're seeing here is our 3D bioprinting, and you can see as a 3D printer, it can print a curve. This is a laser-based system that we developed in-house. And as I mentioned, the uniqueness here is that it can deposit cell by cell, and this way we can receive integrity of the tissue as it is in the body. When we talk about the 3D, and we're not inventing anything here, when we want to print this vase, so we take a 3D image, and we put the picture into the computer, and then slice it to 2D, and we build it layer by layer. The same approach comes here, the same exactly in a tissue in the body. And if we look, for example, at the cornea, and this is the structure of the cornea, we can see there are layers. So we can essentially do the same process, put a layer of cells, a layer of another material, another layer of cells, And this is the same concept of any 3D printing. And here, essentially, we're utilizing the, I would say, the evolving area of 3D printing into the biology. The process that we developed in Precise, essentially, as I mentioned, starts from the cells, starts from the sourcing of the cells, and they can become, and it can be from stem cells, it can be induced pluripotent stem cells, it can be embryonic stem cells, and it can also come from a biopsy from primary cells that we take from a patient, and then we'll have the patient's own cell, so the body will not reject it when we transplant it in. We can also take from one source of cells, one cornea, and expand it to enough cells to fabricate 100 corneas. Here we develop technologies of expansions of the cells, and it's important also that we can freeze them and take them out when we want, because we're thinking of a supply chain. We're not just thinking of putting it one time and doing it manually, but really to be able to provide a sustainable and supply chain of tissues and organs to the patients. As I mentioned, we also have the bioink. The bioink is the ECM and other materials that help us throughout the printing process or fabricating process as cross-link materials, but they also help us maintain the viability of the cells throughout the printing process. And if you think of your printer at home, you have RGB, so red, green, and blue. So in our printer, we have endothelial cells, epithelium cells, cardiomyocytes, hepatocytes, depends on which type of tissue or organ we want to fabricate. And that's the biofabrication process. But we have the cells there and the material there, it's still not a functional tissue. And here, what we call the fourth dimension, the maturing phase, where we put the tissue in a bioreactor, and we have from cells, single cells, essentially we're able to achieve a functional tissue. And of course, we don't forget at the end that we're putting a tissue in a patient, and we want to be sure that this tissue will function. We have a QC process from the beginning, from the cells, all the way through the fabrication. And at the end, before we transplant that tissue into the patient, we're sure that it will function and be safe. So this is the theory. And I'll just show, and as other presenters said, that we have limited time, so I'll just show a few examples of tissues, and these are just from part of our preclinical studies of tissues that we fabricated. We started out from the cells, did the whole fabrication process, transplanted them in animal models, and they function. What we're witnessing here, and at the bottom we can see here an eye of a rabbit that has a disease. We mimic the disease. In the middle, we transplanted the tissue. We can see as it adheres to the inside of the cornea of the rabbit. You can see here on the right the cells. These are human endothelial cells, and the result is that this rabbit can see. If I connect to the previous talk, so we have to ship it around the world, and we developed methods to freeze it, take them out of freezing, thaw them out, and we can ship these around the world. Some of the transplantations we have done, we fabricated in Israel, sent them to the US, back to Israel, and transplanted them. Another example is here a tissue that essentially can shape the cornea, and we're showing here 3.5 months of follow-up, where if there's a disformation of the cornea, we can reshape it and think forward. Instead of glasses, we can shape the cornea. Instead of laser procedures that not everybody is eligible to have them, we can do that. And here we're showing that we can shape it essentially with any standard laser system that is in most of the eye clinics in the world. Last but not least, and we are building a pipeline in the ophthalmology field, we're witnessing here a 2 months follow-up of a retinal tissue transplanted in a porcine eye. And these are just first time that we're presenting these results. It's just recently. This is our pipeline for the future. Everybody is familiar with AMD, age-related macular degeneration, which is one of the leading causes for blindness, and this will be able to bring a solution for that. So, as I mentioned, we're starting out in ophthalmology. In the future, we will be addressing other areas. Technologies will be evolving, the biomaterials, the bioprinting, and other technologies that are needed for these, to bring these tissues to the clinic. And this is the beginning. But in the future, we will see, and if we look 10, 15 years, we will see bioprinted hearts, kidneys, and other organs. Thank you.
Please welcome the Right Honorable Tony Blair.
Thanks so much.
It's really too bad you couldn't.
By the way, I was just listening to the presentation on the bioprinting and reflect. I hope that develops fast because I could do with a bit of that.
Yeah, we're seeing lots of really amazing technology today at the conference.